This is video 32 in the lecture on the design of reinforced concrete beams. This lecture explains how to deal with torsion in a reinforced concrete section. We have two types of torsion. The primary torsion is the equilibrium torsion, and the secondary is the compatibility torsion. The equilibrium torsion is important in ULS. It has to do with the resistance of the structure, and it is a static equilibrium. The compatibility torsion has no influence on the global stability. It only plays a role in SLS. An example of equilibrium torsion is when you have a bridge which is asymmetrically loaded, then you will have a torsional moment in this direction. Or if you have a beam with slabs supported on the beam, and if the span on the left-hand side is different than the span on the right-hand side, then you also have an equilibrium, or you need an equilibrium, and that equilibrium is given by the resistance to a torsional bending moment. Or you can have a beam which is eccentrically loaded by, for instance, brickwork or masonry, then also you will have an equilibrium torsion. An example of compatibility torsion is when you have a beam portal system like this, then you will have their compatibility torsion. The same happens when you have a continuous slab ending in your beam. There is also in fact a compatibility torsion. The general concepts and analogy. Tau is the torsional shear stress. You can compare it with the shear stress under bending. G is the gliding modulus. You can compare it with E. And the sliding modulus is related to the modulus of elasticity to the coefficient of Poisson nu. We have the strain gamma, the torsional moment, and the polar moment of inertia. Just to refresh your memory, in fact, the polar moment of inertia is for most sections equal to 2 times the moment of inertia, the normal moment of inertia. For instance, for a square, the polar moment of inertia is a to the power 4 divided by 6, and it's 2 times E. Same happens with a circle. It's P8 to the power 4 divided by 32. It's also 2 times E. And you can now easily see why, or it gives you an idea why. You have the polar moment of inertia for rectangular. It's AB to the power 3 divided by 12 plus B8 to the power 3 divided by 12. It looks like you have 2 axes, and about those 2 axes you have the normal moment of inertia, and you add them up. So that explains a little bit where the 2 is always coming from. And then we have the torsional modulus, WT. The surface AK is defined as the dotted line is the midsection, and the surface of the area enclosed by the dotted line is AK, and the width of the section is T min. And then we know that the torsional modulus WT is 2AK times T min. Torsion of prismatic cross sections. Tau is G times gamma, with tau torsional shear force and gamma the strain. You can compare it with the classic formula, sigma is epsilon A. This is in fact the same type of elements. Gamma is air times alpha. Alpha is the angle of twist per meter, and alpha is then the torsional moment divided by GEP. And you can compare this with M over AE equals epsilon over V for bending. It's a similar type of equation. The stress is then tau r divided by IP, and r is the radius, and EP is the polar moment of inertia. You can compare it with sigma is mv over E. And tau max is T divided by WT, with WT the torsional modulus, and you can compare it with sigma max is M divided by W. So now you have a comparison or an analogy between those two, between torsion and bending. The relation between torsional moment and torsional shear stress is as follows. If you have a cross section, you have the point of gravity in the middle, and you have the radius A. A is not a constant, it's varying. And you have the width T, which is also varying. Then you have a shear stress tau alongside the section, and tau times T must be a constant, and this constant Q is called the shear flow. So tau times T is a constant and is a shear flow and depends on the torsional bending moment. So the torsional bending moment equals the tau times T times A. It's A, it's in fact this force times A, and then the line integral dl, the line integral dl, and then you see tau times T is a constant, is Q, is the shear flow, and this element, the line integral of A dl, is of course equals 2 times the enclosed surface AK, which is the enclosed surface of the midline of the section. To give you an idea, if this is sounding strange, if you take a circle, the line integral of the radius of the circles times ds, well, the radius is then constant because it's a circle, so r is outside, and the line integral of ds is of course the circumference of a circle, which is 2πr, and so we have in fact 2πr squared, or 2 times πr to the power 2 divided by 4, so it's 2 times the surface, or yeah, it's 2 times the area. So that gives you an indication where the 2 is coming from. So we must remember that the torsional bending moment equals 2 times the area AK times the shear flow. AK is defined as the area between the dotted lines, and the dotted lines is the midsection. For a torsion of tubular cross sections, we use the formula of breadth. Now we will understand this formula. We know that the shear force Q is tau times T, and that T was equal to Q times 2 times AK. If you combine those two, then you see, and you solve it for tau, for the shear stress, or for the stress, for the torsional stress, tau max is then equals to T divided by WT. If you look now at the compression stress due to torsion, then we see that the force in the compression stress is the shear flow divided by the sinus of theta, with theta the angle of the shear stress. Q we know is tau times T, and T is 2qAK, and then we can solve it, or we can calculate the stress, the concrete compression stress, which is the total compression force divided by the area, or by the cross area. And if you work this out, then you will see that we obtain this formula. For theta equal to 45 degrees, we see that the concrete compressor stress equals the torsional moment divided by TAK, which sounds acceptable, which sounds what we expect. Then for the reinforcement, we have the stirrups and the longitudinal reinforcement that plays a role, the same as in shear force. For the stirrups, the force in the stirrups equals the shear flow, of course, and equals N times the cross section of the stirrups times the yield stress. We know what T is, what N is, and if you substitute it, then you see and you solve it for ASW over S. So this is the amount of stirrups you need to take a torsional moment T, which is related to the surface AK. And if you look at the longitudinal reinforcement, then if you take UK, which is the circumference of AK, then the force that has to be taken by the longitudinal reinforcement is UKQQ times cotangent theta, and that force must be equal to the force in the reinforcement or the additional force in the reinforcement, and you solve it for ASL, you have this equation. So for torsion, you have an additional stirrups and you have additional longitudinal reinforcement. For equilibrium torsion, we have reinforcement for torsion plus additional stirrups plus additional longitudinal reinforcement. But we should not forget that the additional longitudinal reinforcement is not only on the tension side of the section, but it's in the whole circumference of the section. So we must not forget that. Then we have to check shear force and torsion together, bending and torsion together, and minimum reinforcement plus torsion together. And for the minimum reinforcement, we must also check the minimum reinforcement needed for torsion. For compatibility torsion, then only the minimum stirrups and longitudinal reinforcements for crack control suffice. It's okay. A plane cross-section is transformed in a tubular cross-section with a fictive thickness. We've seen the formulas for tubular cross-section, and now we can transform a plane cross-section into a tubular one with a fictive thickness. Let's suppose T is the design value of the torsional moment, and tau is the torsional shear force, and VED is the shear force due to torsional moment. Now, for clarity, the total area enclosed is A, and the circumference is U. And the total area within the midlines, if I can put it this way, is AK, and the circumference of AK is UK. So don't mix them up, those two. The fictive thickness of the plane section is equal to the total area A divided by U, by the total circumference, and must always be bigger than 2 times D1, and D1 is the point of gravity of the longitudinal reinforcement. So the fictive thickness is the total area divided by the circumference and must be bigger than 2 times the D1. Cotangent theta must be between 1 and 2.5. We see that the shear force due to the torsional bending moment is equal to this, and if we substitute, then we see that the shear force coming from the torsional bending moment is the torsional bending moment divided by 2 times AK, which is a little bit logic, times ZE. And for the stirrups, it's we have seen ASW over S is equals this, but VED1 is what we have seen now is this element, and you can transform it to this formula. This is the stirrups that you need due to the torsional bending moment. And for the longitudinal reinforcement, the force in the total force in longitudinal reinforcements is equal to this, and you can work this out. You substitute, and you have that the total longitudinal reinforcement, that's the sum, so it's the total, it's all the whole circumference is the torsional bending moment divided by 2 AK multiplied by UK and divided by the yield stress and cotangent theta. We also have to check the concrete compression of the strut. That means that we have to check the VRD max and the TRD max. For shear force only, it is only VED divided by VRD max that we have seen must be smaller than 1. But now we have to combine it with torsion. So we have to comply now on this to this equation. TRD max, we haven't defined this yet, but it's equal to this. Nu that we know already. And for the check if we need reinforcement, then we see that we must check the equation that VED must be smaller than VRDC for the shear force, but now you have to do the check for both together at the same time. So this equation counts. And TRDC was not defined yet, but is defined by 2 FCDD TEF times AK, and FCTD is the 0.05 limit of the tensile stress in the concrete, and is equal to 0.7 times FCTM. You know now that you can handle torsion by adding stirrups to the stirrups needed for shear force. See you at next lecture with an example.